In this unit, we've been studying differential equations and how to solve them to find their general and particular solutions. In this lesson, we'll take a more visual approach and use slope fields to represent differential equations and their solutions. A slope field is going to give us a graphical representation of what a differential equation looks like and also produce a family of general solutions, which is what we get when we find the antiderivative and add our unknown constant c. The way that we're going to construct these slope fields is to draw a small segment of the tangent line at each point. And we know that at each point, the slope is defined by dy dx, and that will give us the slope of the tangent line at each point. So before we start drawing some slope fields, I want to talk about just some general rules about how the slope should look when you find dy dx. So if you get a dy dx equal to 0, you're going to make a horizontal slope. If you get a slope equal to 1, that's a 45-degree angle. So that should be increasing with a slope of basically a rise over run of up 1 over 1. So that gives you that 45-degree angle. If you get a slope greater than 1, it should be a steeper angle, so increasing more steeply. If it's less than 1, it should be flatter than that 45-degree angle. And if it's negative or less than 0, instead of an increasing slope, you should have a decreasing slope through that individual point. And the other kind of specific slope that you might get is an undefined slope. And often we don't show that on the slope field because that slope actually does not exist. Some textbooks or problems that you will see, they will draw the slope field tangent line as a vertical line. So just know that those two options are something that you might come across. When you're asked to construct a slope field on the AP exam, they'll give you the differential equation, and then they'll give you a graph with only certain points highlighted. So you'll see we have 9 points here. So each of the points that's highlighted in the graph that you're given, you'll have to find the slope for and draw in the segment of the tangent line that we spoke about. So you won't be given this table here, but it's a good place to start to kind of collect your data points for each of the points that you'll need to graph the slope field for. The first thing we need to notice about this differential equation is that it only has the variable x in it. So the slope will only be controlled by the x value, not the y. So in this particular graph that we're given, we only have x values that go from -1, 0 to 1. So that's going to control the value of dy dx, and so we won't need all the values in this table. So to find the value of dy dx at each of those x values, you just one by one plug the x values in. So when x is -1, your dy dx is going to be -2. When x is 0, dy dx will be 0. And when x is 1, dy dx will be 2. So now that I have the values of dy dx, I want to show those on my slope field by graphing those as slope values at each of these x values. Let's start with 0 because that is an easy slope to graph since it's going to be a horizontal slope. So whenever my x value is 0, my slope is going to be 0. So the x values of 0 happen on the y-axis. So at each of those points, I'm going to draw a small segment, for some reason that's a tongue twister for me today, of a slope of 0. So you'll see that it doesn't need to be a large segment. You just need to show that it's a horizontal slope at each of those 3 points. At x is equal to 1, that slope is going to be +2. So when I go over to this column of x equal 1 values, I want to think about making a slope of 1, which is at 45 degrees. And then we talked about if it's greater than 1, I should go a little bit steeper than that. So I'm going to estimate a slope of 2 at each of these points where the x value is 1. Please know that slope fields are not an exact science. They're just going to be looking for your slope to be going in the right direction, specifically with horizontal slopes, and then positive versus negative slopes. So in our last column where x is equal to -1, we came up with a dy dx slope value of -2. So I'm going to make it a little steeper than a 45-degree angle, but make sure that I slant it in the decreasing direction for each point. So what we're looking at here is at each point, we're looking at the slope of a function y whose derivative dy dx is 2x. So what I'd like to do is go through the process of solving for y, both the general and the particular solution, so that you can see this slope field also shows us a picture of what our solution looks like. Finding the general solution will give us a good chance to practice our two basic steps of separating and integrating. So I went ahead and got started by multiplying by dx on both sides, and that quickly separated the dy on one side with the 2x dx on the other side. When I found the antiderivatives of both sides, I got y equals x squared, and I remembered my unknown constant c because this is an indefinite integral. And so we're starting to see what the solution will look like. This is our general solution, y equals x squared plus c. And we know that x squared plus c is a parabola that may or may not have been shifted from the origin. So if you look at that slope field, I hope that you'll start to see a pattern of what looks like a set of parabolas. And remember, it's a set of parabolas because what we just found was a family of general solutions. So if we were to graph even more points on the slope field, we would see an infinite number of parabolas develop. So what I'd like to do now is take our general solution and use it to find a particular solution that goes to the point 0, 0. So we'll take those values and plug it into our general solution to find c. Sorry, I had an extra square there that I didn't need, so I whited that out. And when I put the 0 in for x and y, it comes out to be c equals 0. So in this case, our particular solution is y equals x squared plus 0, or just y equals x squared. And so that equation, of course, is a parabola that goes through the origin, which we knew because that's what we were given. So a lot of times on the AP exam, after you're asked to draw a slope field, they'll ask you to draw a sketch of a solution curve that goes through a particular point. So we'll use that point at the origin 0, 0. And basically you only have two jobs to get this question right on the exam. First, you have to go through the indicated point, so that should be pretty obvious. And the second is you have to draw a curve that goes with the flow of the slope fields. So in this case, since I know it's a parabola especially, that should be pretty easy to do. So as long as I go through that indicated point and go with the natural flow of the slope field, I'll get all my full credit on that question. So you may have noticed since our differential equation just had the x variable in it, we had slope fields that all of the columns were the same. And as you might imagine, if the slope field the differential equation depended only on y, all the slopes in the rows would be the same. So that's an important pattern to recognize. Now, if the differential equation has both x and y in the equation, all of the slopes at each point will be different. You may still be able to find a pattern, but just know that you'll have to test each point. So when we get to back together in class, we'll practice some that depend just on x, just on y, and then one that depends on x and y. And after we practice drawing some more slope fields, we will actually practice matching slope fields to equations because that's a common multiple choice question on the AP exam. So I'll see you then.